Hi everyone, wish you all a very happy new year and welcome back to my channel. So today I'm going to be talking about a different paradox which is based on a thought experiment performed by Thomson, and it's known as Thomson's lamp. So what we do in this thought experiment is we imagine a lamp that we turn on at t equals 0, and then at t equals 1 minute we turn it off. Half a minute after this point we turn it on again, and 1/4 of a minute later we turn it off again. So we keep continuing this process of turning it on and off, and the time gap will be 1 by 2 power some natural number as per the series 1 plus half plus 1 by 4 and so on and so forth. And you will see that this ultimately reaches a point of 2 minutes because this infinite series 1 plus half plus 1 by 4 and so on and so forth is actually an infinite geometric progression. And so if I write it down here, so if I say 1 plus half plus 1 by 4 and so on and so forth, it's going to converge to be a over 1 minus r, where r is a common ratio. So it will be 1 over 1 minus half, which will be 1 over half, which will be 2 minutes. So ultimately I'll reach this point of 2 minutes, and that's where this sum of this infinite series is going to go. So what do you think the state of that lamp will be at t equals 2 minutes? Will it be on or will it be off? So suppose I say I have done this operation an odd number of times as t tends to 2 minutes. The bulb must be on. On the other hand, if the number of operations I carried out was even, so when we did this experiment, the first time it was on, the second time it was off, and so on and so forth. So for every odd trial, the bulb ended up being on, and for every even trial, the bulb ended up being off. So when we approach this 2 minute mark, will it be an odd number of trials or will it be an even number of trials? Turns out that you can't say for sure whether it will be an odd number of trials or an even number of trials. And this is obviously because of the inability to assign a certain value to, or rather a certain parity to infinity as being even or odd. So actually, as I've mentioned here, it's a super task. So what a super task is you try to perform a countably infinite number of tasks in a very directly countable time frame. It's not an infinite time frame, but a countable time frame. It's a usual time frame, finite time frame rather. So when you try to perform a countably infinite number of tasks in a finite time frame, you can't exactly decide the parity of the final leg of the tasks. And here's what I mean by a countably infinite number of tasks. There are two kinds of infinity basically. There is countable infinities and there is uncountable infinities. So countable infinities are actually sets, infinite sets of a discrete number of discrete values. By which I mean you have 1, 2, 3, 4 and so on up till infinity. You have all these natural numbers, but then you have a clear demarcation as to what belongs to this set. So you can say 1 belongs to this set, 2 belongs to this set, and so on and so forth. And the number that comes after 1, immediately after 1, when you arrange them in ascending order, will be 2. On the other hand, if we take a set like the set of real numbers, you don't exactly have a specified ascending order for this. So you can't say that right after 1 in this list I'll be able to put 2, because there's an infinite number of real numbers right between 1 and 2. And even if you take 1 and 1.10000001, there's still 1.0000 something that's lying between these two numbers. So the first set that I talked about is just the set of all natural numbers is a countably infinite as a set with countably infinite cardinality. On the other hand, this set of all real numbers has an uncountably infinite cardinality. So Thomson's lamp involves a certain set of discrete tasks, right? So after the operation at t equal to 0, we are going straight to t equals 1. And after that, we are going straight to t equals 1 plus half, which is t equals 3 by 2 minutes. So we know where we are performing these tasks. So there's not an infinite number of tasks that lie between every two tasks. So the number of tasks is still countable, but it's just infinite. So this is performing countably infinite tasks in a finite time frame. And that's what Thomson's lamp is an example of. And something that's related to this super task is nothing but this very beautiful series 1 minus 1 plus 1 minus 1 plus, and so on and so forth. And you can see that when I take the sum of this series to an odd number of terms, if I add up if I take the first term, it's obviously just 1. If I take the first 3 terms, it's 1 minus 1 plus 1, which is again 1. And if I take the first 5 terms, it will be 1 again. On the other hand, if I take an even number of terms, if I add the first 2 terms, I get 0. If I add the first 4 terms, I get 0 again. So whenever I take up an even number of terms of this infinite series, this is an infinite series by the way, and if I take an even number of terms of this infinite series and add them together, I get my answer to be 0. So this series has a similar answer. This can be considered as a mathematical way to think of this thought experiment, which is none other than Thomson's lab. So suppose I say on is 1 and turning it off means I add minus 1 to the series, and the state of off is described by 0 and the state of on is described by 1. Let me repeat this, it might sound a bit confusing. So when I turn it on, I add 1. When I turn it off, I add minus 1, so that the state of being on is described by 1 and the state of being turned off is described by 0. So what happens is, when I turn it on at t equals 1, which is the first operation I'm performing, this series takes a value of 1, which means it's on, actually, obviously. And now if I turn it off as at t equals 3 by 2, which is half a minute after the first operation, I subtract 1 and now my series sums up to be 0. So after every even number operation, the sum of this series is 0. The funny thing is, the sum of this series, when you take it mathematically, is not going to be either 1 or 0. Because what you can do is, you can take up this sum and write it as 1 minus 1 plus plus 1 minus 1 and so on and so forth. So it's actually whatever is inside these brackets is none other than s, which is the original sum that we took. So you can say s equals 1 minus s, which means 2s is 1 and s must be half. And this is increasingly funny. It's incredibly funny because you have a series in which when you take a finite number of terms, the sum is going to be either 1 or 0. But if you take an infinite number of terms, the sum turns out to be half. And this reminds me of something, which is Schrodinger's cat. When you observe the cat in the when you think of the cat which is inside the box without opening it up, it can be either alive or dead. In fact, it's in a superposed state of being alive and being dead. On the other hand, when you open it, you can observe it only in one of these two states. An infinite series can be thought to be like that. So when you say I have this infinite series, I don't know how many terms I've taken, and if I add all of these together, I get half. It's a superposed state. On the other hand, if I know how many terms I'm examining, when I stop the series at a certain point and I say, okay series, you can stop now, and then I examine it, its value depends on whether I've got an odd number of terms before or an even number of terms. And this is very beautiful. So since we are talking of a lamp, there's one more thing that I'd like to mention. The sensation of sight that we have helps us distinguish colors as well. I believe that's something called rods or cones. I don't know which one of these is helping us distinguish between colors, but there are some things in our eyes, all biological things, which help us examine color and distinguish between two different colors, distinguish colors. But can I say for sure that what I see to be blue is the same as what you will see to be blue? So how do I even describe a color without comparing it with another color, another thing of a similar color? It's a very related thing to describe, isn't it? So you can't say for sure. In all probability, what I'm seeing as blue might be seen as orange by somebody else. It all depends. And that's really amazing. I hope you all enjoyed this video. Stay tuned for the next one.